normal curve. Can you remember that we had to find things like what percentage of people had a z-score, let's say, greater than 1.9? You remember that type of question? It was in 6.2. And it was really all done on calculator. So it was normal CDF, okay? And there was 4 numbers, but weren't the last 2 numbers 0 and 1? And this was 0 because that's the mean of a z-score, and this is 1 because that was the standard deviation of the z-score. And I guess for completeness sake, I should fill in the other 2 numbers. If you want to know what percentage of z-scores are greater than 1.9, does 1.9 go here or does it go here? Because that's your only choices. Does it go first or does it go second in this question?
First.
Okay. And I made up a executive decision number for the second guy, didn't we? Can you remember what my number was? But you could use almost any number you like.
999.
999. Right. Which is how you phone the emergency services back home. Which now brings me to a joke. Why can't Polish people dial 911? You don't know? They can't find the 11 button. Did you just shake your head at my joke there, Jenna? Is that what you just shook your? Yeah. Okay, I'll remember that when I'm grading now.
Only because my kids do the same thing.
What? Oh, it looks like you got one behind.
Yeah.
Yeah, you've got one behind you right now. Okay. Just for completeness, I'm going to go through 3 versions and then show you the upgrade to it. Now, if you were doing this one, it would also be a normal CDF. But this time we're looking for z-scores less than 1.9. If you want to do less than 1.9, the 1.9 goes second. And what do we fill in with the first number? Yes, I see your lips moving, and that's what I think she was saying. Right, 9, give 999. We're quite comfortable with these 2. And for completeness sake, then there is only one last version, isn't there? You can be bigger than this, you can be less than this, and then the last version between 2 numbers kind of version. So say -1 to positive 1.3, you know, that kind of question. In this case, you're going to use a normal CDF. In a lot of ways, isn't this the easiest of the 3? Because doesn't the first number go first and the second number go second? Now, when you did these are the percentage of z-scores bigger than, less than, or between 2 specific values. Doesn't the calculator always give you a decimal number like 0.123, but we almost always convert that into a percentage. So it might say 0.12, but we typically think of that as 12%, because I think humans, 12% is easier to understand, right? 12% of the time you get a z-score bigger than this or less than that. So far, so good. Now, suppose I have a population and the mean is 65. So let's say that for the population, the average height is 5'5", and that the standard deviation is 6 inches. And I would like to know what percentage of people have a height, so X is the data, have a height greater than 69. Now, in section 6.2, didn't we have to turn that into the equivalent z-score and then do this? The good news is you don't need to, because we're now going to find how to get the area under any normal curve, not just the standard normal curve, but any of them. So if I draw a little picture just to visualize what's going on here. there's your normal curve. Would you agree that this guy is 65, right? If I just do one standard deviation, that's 71. If I do one going the other way, that's 59. That's just like reference points. If I now put in 69, it's a bit like here, right? And aren't we trying to find out how much of the piece of cake, right? What percentage of the cake the shaded red bit is? And we are going to use a guy that we already know how to use. We are going to do a normal CDF guy. And it's going to be low number, high number, mean, standard deviation. So in this question, there are going to be two numbers. The mean is going to be 65, and the standard deviation is going to be 6. So do you see all we do is replace the 0, 1 by the mean of 65 and the standard deviation is 6. Now, if you want to be bigger than 69, think of what we did when it was bigger than a z-score. Don't you put a number here and another number here? And let's see if that kind of makes sense. Where should the 69 go if you want to find something bigger than 69? First or second?
First.
Now, what kind of executive decision number do you put here?
999.
Do you see why 999 is probably more useful now for these questions than it was for a z-score? Because seeing a z-score, couldn't you make that 5 and you get the right answer? Because z-scores of 5 are so unusual, you've pretty much done it. But can you see in these questions here, you need a big number, right? Now, sometimes you have to alter this second number. Can you imagine you're talking about a mean of 65,000 and a standard deviation of 2,000, right? Can you imagine data that had 65,000 mean and, 2,000 standard deviation? Wouldn't this number have to be like 8 nines or something just to be sure? So you just keep adding nines till you're happy, really. And then at this point, we then need to switch over and remind you how the calculator works. So if you can bear with me, I am about to get a chat here. Some person just had issues with their cat or their dog or both. Okay. So I'm going to share my calculator with you. If you've got one handy, it probably would be a good idea for you just to, press the buttons along with me. So I'm going to switch my calculator on. Can anybody remember where normal CDF is? Because you got to find the thing, right? So just tell me the buttons to press to get it.
Second distribution.
Okay. Now there's a lot of choices here. Who's our guy? Which number? 1, 2, 3, 4. Which one?
2.
2. Okay, so it wasn't hard to find, right? Great. Wasn't hard to find. Now, we got all the numbers. We want bigger than 69. So 69, comma, 999, comma, the mean, which is 65, comma, and the standard deviation is 6. And the decimal answer that came out was 0.252 to 3 decimal places, which I'm now going to convert to 25.2%. Would you all agree that's actually a little bit easier than turning it into a Z-score and then doing it, right? It takes one whole chunk of work away from you. Right? It never ceases to amaze me that if you know the shape is normal, right? Mound-shaped, bell-shaped, whatever term you choose to use. If you know it's that shape, or at least approximately that shape will do, and they tell me the mean and standard deviation, can't I find percentage anything? Can't I find a percentage of people who are 6 foot tall or bigger? Percentage of people who are less than 48 inches? Percentage of people between 39 and 71 inches. By simply using this really cool function here called normal CDF. The textbook doesn't necessarily tell you to do it that way. And if you look over the textbook, they use a table of values, which is basically just a big page of numbers that tells you the answer. But for those questions, you have to convert them to Z-scores. And so we're doing the modern way of doing it, right? We got the technology. Why should we, you wouldn't do a Z-score in this question now. Now that you know how to do it without Z-scores, agreed? Right. On section 6.2, they showed you the Z-score method, and that's fine. It's cool, and it does have advantages, right? If I know what the Z-score is, don't I get a good idea of how unusual that number is? Right. So if I get a Z-score and it's 3.8, oh, you're a Bill Gates, you're an outlier, right? If I get a Z-score of -2, doesn't that at least tell me you're less than the mean and you're quite low in the, the totem pole of values? So Z-scores do convey information. But given this particular process, can you imagine that there's only going to be 3 standard questions? Bigger than 69, less than 69, or between 2 numbers, right? Agreed? Just like bigger than Z, less than Z, between Z. Do you see that there is a direct link between how you did this and how you're now going to do the new stuff, right? So I am going to give you, right out the bat, without any real practice, right, chucking you in the deep end, 3 guys to do on your calculator. So the first one is, I want to find the percentage of people. I'm going to do my favorite IQ one, right? So it's 100 and the standard deviation is 10, right? What percentage of people have an IQ of 130? I believe that's normally called the genius level, right? Depends who you ask. The second one is X less than 80, and that's called the football level. No, it's not. I just made that up to insult them. And then the third one is, what percentage of people have an IQ between 92 and 103? Okay, go for it. Use your calculator. Hopefully you've got one. You've got one in your phone, you've got a physical one, or you've got an online one of some kind. And I'm only giving you 3 minutes.
Mr. Robinson,
Yes?
it's me, Leah. Question.
Uh-huh.
Well, not a question, but a statement. I was going to let you know in like a few minutes, I was going to log out of my cell phone and log back on my computer. I have
So let you in?
Yeah, so let me in when you have an opportunity. I'll let you know. They told me that I just seen the email this morning that the school's power went down. So any person who's borrowing a laptop from the school is not going to properly work until a little after 10 o'clock, which is about that time now. Just to let you know.
Okay. Thank you. Yeah, I was told that the internet's down, but evidently the internet's down because the power was down.
Yes.
So evidently the power was down because somebody was digging a hole somewhere that they shouldn't be and they cut the power cable. That bit I'm adding on, right? I have no idea, right? Why it's down. Okay, I'll let you get on with what you're doing then.
Okay.
And I'll let you in a few moments.
Okay, thank you.
You're welcome. You look like you're done, Jenna, or do you not have a calculator?
I'm done.
Whoa, God, you're fast. You know how to hit those buttons.
I only know if I'm done if I have the right answer though, so hopefully we'll see.
Well, you're done. One way or the other, you're done. Right. Actually, it'll give me time while everyone else is finishing off for me to okay, looks like I'm done. So you're going to have to volunteer an answer, and then if we get thumbs ups, we're going for it. So don't worry if you get it wrong, because you know me, I make mistakes too, so it's no biggie. Anybody want to volunteer the first one, which is what percentage of people have an IQ greater than 130? And this should have been the normal CDF instructions. What's the answer?
I got 0.1%.
Yes, because it's geniuses and it's tiny. So that doesn't surprise me, 0.1% or 0.001 if you're looking at the decimal. Do I get a thumbs up on that?
Just a question, Professor
Yes.
Robertson. Do you want us to put it in the percentage or
I
leave
would.
it in
I like it as a percentage. Now, whatever the homework tells you, you do
whenever they
it, right?
ask? Yeah, okay.
So if the homework wants decimals to 3, you give it to 3. I
Okay.
just like percentages. It's easier to see. Can you see how rare a genius IQ level is? It's about roughly 1 in 1,000 people, right? So if you know 1,000 people, one of them's a genius, unless you know a lot of really clever people. On the other hand, if you hang out with football players, you won't find any there. So, has anybody any idea why I pick on poor football players?
Because they all have head injuries.
Oh God! Oh, you're adding to it now. I just feel that the stereotype, which is totally untrue, I'm sure, is that they're not too bright. But actually, the stereotype depends on what position they play. I think quarterbacks have to be very physically fit, but don't they also have to have sharp reactions and have a brain, even if it's a spatial brain? Not that it's a bad brain to have, but a spatial brain, right? Spatial awareness and tactical awareness brain. So they definitely have to. But on the other hand, if you're one of those big, strong, heavy guys, isn't your only job grab guy hurt? I mean, there's not an awful lot of process that you need to worry about. So that's the ones I'm picking on. Okay, move on to the second one. Here's Lee. Give me an answer and we'll double check it. That last one seemed to work. Anybody want to volunteer it? Zoe?
I got 2.28%.
Okay. So as a decimal, that would be 0.022 and 8. Does that look good? 2.28%. Anybody not got that? And okay, we got time. Let's find out. Don't worry if it's not right. As I say, it's so easy just to hit the wrong number somewhere. So I'm going in. I do number 2. I've got negative 999, a comma, 80, 110. 80, a mean of 100, A standard deviation of 10. That's 0.0228. You nailed it. That's exactly what I have. So about 2.25% of the population have an IQ less than 80. And then last but not least, has anybody got an answer for the last, the middle one? The last one, that's fine.
0.46.
Right, so we're looking at about 46%. How's that look, guys?
Should be about 41%.
41%?
Yeah.
I got 41.
41 it is then. 41 gets the job.
Mr. Robertson, I'm transferring from my phone back to my laptop now. Would you
So
be
I'll
able
be
to let
ready
me in?
for you in a minute.
Yes,
Right.
sir.
It looks like Leah got through, so internet is up and working and whatever
No,
they need to do.
no problems, thank God.
Okay, yeah.
I have a quick question for number 2.
Yes, Rachel won.
So, or 2, it can be Rachel too. I don't care. So when it's x is less than, it's always 999 is always going to be negative, right?
Yes.
It's going to be okay. I just want to verify, just double checking.
So it's easy to remember. When it's less than, negative. When it's greater than,
It's always
it's
okay.
positive. And you got to remember the order, right?
Right.
You know, which one goes first and second. But negative
Right.
999 is pretty obviously going to be first, right? And
Right.
positive 999 is pretty obviously second. So you know what.
Okay.
And I don't think you have a problem that mean standard deviation.
Yeah, no, I just wanted to verify, like,
Yep,
just
we're cool.
double-
You got it right.
Awesome. Thanks.
Okay, so let me kind of ask a question and tell you how we solve this question. And this is the question. How do we check that a distribution is normal? Because for all of what we're about to do, doesn't it have to be symmetric, bell-shaped, mound-shaped, normal, right? It has to have that shape to work. If the data has that shape or roughly that shape, we are good to go. But we don't like skewed, especially badly skewed, right? So we don't like them. If we did it with that, right? Because this distribution, all distributions have means and standard deviations, right? They all have them, right? But if I did what we're doing to this distribution here, and can you imagine that we were trying to find, let's pretend this number's 100. Can you see in this case, the 100 would be that much? Can you see in this case, the real answer would be a lot more than what that would be. So what happens is that if you try and use the, I'll call it the trick, right? The process that we're using, right? The normal CDF. If the thing is normal, you can take your answer to the bank. It's going to be right, minor differences, but it's going to be right. On the other hand, if your data is not nice, right? If it's skewed left or skewed right or just wobble, double hills or anything, and we shouldn't be doing that. So the question is, how do we check it? Well, couldn't you just take all the data and make a histogram of it and then look at the shape? That would be a reasonably clever way to do it, right? And if it looks skewed, you probably shouldn't use this process, right? You should do other techniques. If it looks nice and symmetric, you should. You can do it that way. There is another way that you can do it. And you tend to do this when you only have a sample of data. So you don't have the entire population to make a picture of, right? All you've got is a little sample of, say, 20 numbers. And you still want to use that information to make predictions on what the whole population would be like. So can you imagine you've got 20 numbers, right? I'll put in some numbers, 1 and 7, and you finish with 92, right? And let's say it's 20 numbers. You can't really draw a histogram well with 20 numbers. Would you agree that there's just not enough numbers for you to get any kind of clarity? And you probably, especially if the numbers range a lot, aren't you probably going to have to do intervals, right? 0 to 10, 10 to 20, 20 to 30. And won't that reduce your information because you have to clump things into groups? So pictures are really not the way that we do the test. Thankfully, this is done by software, and you're never going to be asked to do this, but I'm going to show you how it works. Can you imagine that's your data, your X's? You find the mean and the standard deviation, and I'm calling them X bar and S because these are samples, right? And let's just suppose that the mean was 30 and that the standard deviation was 12, right? Just for argument's sake. For every single one of these numbers here, right? From number 1 to number 92, you turn them into their Z-scores. So can you imagine that would involve you doing 20 Z-score calculations, right? Data 1, take away the mean 30, divided by 12, and can you imagine that that one might be negative 2.1, that's negative 1.9, and this guy at the end maybe 2.8, and all the other Z-scores. Can you imagine taking the raw data X's and turning them into Z-scores? You with me so far? Then you plot Z-scores against data. And you're going to have a 0, and you're going to have a negative 1, you're going to have a negative 2, and maybe a negative 3, and a 1, and a 2, and a 3. And you plot these two together. And so the X is what? 0 finishes at 100, right? And 50 in the middle. This is what you will get. Do you see that set of dots? Although not perfect, would you agree that they're almost all in the same straight line? If you get a picture that looks like this, you have a normal distribution, and you can do what you're about to do, and you can do it with samples as well as with populations. So we will assume that throughout the homework, this has been done, and that the distribution is normal, so we don't need to worry about checking that it's going to work. We just assume we're allowed to do it and we're good to go. Now, what would it look like if it wasn't normal? You know, like it was skewed left or skewed right or something? You won't get a straight line. There's not a perfect straight line. Life isn't perfect, right? But what you will get is maybe some curve. And if you see a curve in this plot, don't start doing normal CDFs in it. It'll give you answers, but the answers will be totally useless, right? You know, like this picture here, right? The answer from the normal CDF is 2%. The real answer is 12%. You see, you could be miles out, and therefore, if you could be miles out, why bother doing it? It's a bit like somebody saying, you know, what's the answer to this? And you say, well, I'm predicting it weighs 22 pound. And then you go and you do it, and it ends up being 220 pound. That is a difference you don't want to make a mistake to, right? You don't want to have to choose data and use it in a way that's going to give you invalid answers. So we will assume that all our data is normally distributed. And we're now going to assume that you can use the normal CDF, not just with population mean and standard deviation, but you can also use it with sample mean and samples deviation, right? Standard deviation. So that's pretty good. That means we can use it. We can take a sample of 20 people and make a prediction on what the population answer is. Right. So I think I'm going to try this, and I know it's going to take a fair amount of time, and I apologize for, your time is valuable, but I think it's worth it to do. I am going to take your ages, if you want to share them again, and we're going to take that as our raw data, and we're going to use it to predict the average age and standard deviation of people who are at OC, and use it to predict what percentage of OC students are in certain age groups, right? So it's kind of a little experiment from start to finish, right? So anybody in the teens, shout out your teen ages.
19.
Any other teens in amongst us?
19.
17.
17. Okay. Any 20s? Start the 20s amongst us.
21.
21. What are you again?
20.
20. Any other 20s?
22.
27.
And a 27. You know, you don't need to take part. You can keep quiet if you don't want to share your age, and that's totally fine by me. Any more 20s?
21.
Any more 20s?
21.
21. Any more 20s? 30s?
35. I turn 35 tomorrow.
32.
Happy
Oh,
birthday.
happy birthday tomorrow.
34.
32.
That's the 30s gone. Any 40s?
43.
Any 50s?
49.
Oh, 49. Any 50s? And I'll put me in, 64. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we're looking at a sample size of 17. Now, can you imagine that if I tried to draw a histogram with that, there isn't enough detail in there for me to be able to tell if it's normally distributed or not. But I'm not doing it. But can I find the mean and standard deviation and eventually get the Z-scores and plot that little chart? And if I saw a straight line, I'd go for it. So I'm going to pretend I did all that and it worked, right? It's normally distributed. So what I'm now going to do is get the sample mean and standard deviation out of this fella. So let's see if we can, we'll get somebody in the chat in case I get a question. Yeah, happy birthday. So when you're on tomorrow, you're going to hear us all sing happy birthday. Right, Marie? Doris? Okay, she agrees. Rachel's thumbs up. Rachel, you're only doing that because you can't have audio and I won't hear you. Is that why?
Oh no, I would definitely sing with my video on.
Okay. Oh God, I get distracted so easily, don't I? I sometimes sympathize for you. I discovered a long time ago that you got to just teach the way you are. I think if you try and be somebody you're not, then it comes across as artificial. And so if you ever meet me in a non-teaching situation, you'll find out that I'm just the same kind of person. I talk too much and I want to tell you jokes even if you don't want to hear them. So it's a kind of the same place. So right now I'm going to put in my data because I need to find the mean and standard deviation. And then we'll do a couple of quick testers, right, on seeing if this normal distribution thing actually works or not. Okay, so oh, you tell me, what buttons do I need to press to get the data in? Because I have to do the data in first.
Start.
Okay, and number one, edit, and in my case, I've got a whole load of numbers, so I'm going to type them in, and you're just going to tell me at the end you missed a 17 or whatever, and that's fine. In fact, if you see me missing it, shout out and I'll type it in directly after it. So that looks like I've got my first row correct. You might not be able to see it, but that's it. This is my second row now. On to the third row, almost done. Okay, so I got the data in, right? This is a sample, so I want the sample mean and the sample standard deviation, right? Okay, so where's that? Tell me the buttons I need to press to find that.
Stat and then calc.
And number 1. Now, in this calculator here, do you see the little flashing black cursor? Isn't it asking me, where do I get the data? And it's in L1. So how do I get L1 to appear? Because I have to hit 2 buttons, don't I?
Second.
Second,
1.
Agreed. On my thing, it's blue. Are some of you the second's yellow or orange or some other color? It's not a biggie, right? It's just a color. Right, so here goes. And one of these symbols is the mean, isn't it, that top guy there? So the mean is 29.4. So the average age of people in this class is about 29. The typical person in the middle. Right, now, there are 2 standard deviations. There's one called SX and the other called sigma X. We're a sample, aren't we? Right, we're not everybody in OC. We're just a small group of you. So which of those 2 is the standard deviation for my sample?
The SX.
Right, so I'm going to call that 12.7. We cool with that? If for some reason you were the only people in the universe for my story, then wouldn't I use the sigma X, which would be the population standard deviation. You might wonder why there's not a mu and then X bar, right? X bar, but no mu. Isn't the mean mu and the X bar the same number in both situations? Isn't the mean of your sample would be the same calculation if you had the same numbers and it was a population? Aren't they the same? Right. So that's why they only have 1 symbol. Right, now let's do a percentage question. So I'm going to kick back in to the whiteboard and I'm going to see if we can make up some questions and then test them out. Okay, so I would like to know the percentage of people who are older than, I don't know, older than 33, right? I'd like to know the percentage of people who are younger than, say, 23. And I'd like to know the percentage of people that are between 18 and 25, right? So we are going to use our sample, right, our data, and we're going to use it to predict what percentage will be in these intervals. Now, in that top one, I think I'll change my pen color. When I do a normal CDF, 33 or bigger, with a mean of 29.4 and a standard deviation of 12.7. And for this second one, I'm going to do a normal CDF again. If you want to be less than 23, won't you be negative 999, which is what Rachel was talking about earlier, right? And then for this last one, won't it be a between one? Oops, sorry. Could you just randomly pick one of those to speed things up, and then I'll just give you a minute. Don't pick the top one. Well, somebody can pick the top one, but try and randomize it that way. I'll have one of each answer somewhere. If you've got time, do 2, and we'll see what the predicted answer is, and then we'll compare it against reality and see how good or bad the normal CDF does as a job. Okay, time up. I just finished doing the middle one. I hope I got it right. 30.7%. I get nods, I'm going for it. I didn't have time. Somebody tell me the top number and we'll verify it with the others. What kind of percentage did we get up the top here?
39.
Nice number,
39.
39. 39?
Yeah.
Look good. Got nods on that one. What about the last one then, this between one?
18.
I hear
Percent.
18. Right. Are we getting comfortable with the normal CDF calculations now? You just need a story where you know the mean and standard deviation, and then you're going to be asked things like what percentage bigger, less, or between. Now let's do a check on that. Let's do a test. Right, the first one. What percentage of people should be greater than 33? So our estimate is basically 39%. So I'm going to look at my 17, and let's see how many of them are older than 33. So 1, 2, 3, 4, 5, 6. And I get 6 out of 17 of you. And I get about 35%. Well, it's 35 and a bit, but that's not too bad. Do you agree? I'm only doing 17 people. You know, you got to be a little bit generous. Pretty good fit. We agree, a few percent out, not too bad. What about this one, less than 23? 1, 2, 3, 4, 5, 6 people. And 6 out of 17, just by a sheer piece of luck, it was the same number of people. Ends up being 35%. Can you see it was an underestimate, overestimate? But would you agree it's within shouting distance? And what the big advantage is, see if I did a sample of 170 people instead of 17, these guys would start getting really, really close to the real answer. Can you imagine more data, more accurate, right? More people, more numbers, more accurate predictors. Right, so the last one should be 18. So 18 to 25. 1, 2, 3, 4, 5, 6 people. Oh, come on. No. I did not plan this. I got to 1, 2, 3, 4, 5, 6 people. No, it doesn't mean every question is 35. I'm a bit worried about this last one. There's a big discrepancy here. Agreed? And these two fitted quite well. This one didn't do such a good job. What that is probably telling me here is that if I did the Z-score data check, remember the ones where you plot the points? I might not have got a straight line. Our data may have been skewed. My gut feeling is that if I just look at the raw data, which I'm going to call this chunk of data, especially me and maybe that person as well, can you see that out of 17 numbers, I might be a little bit too skewed to the right? I mean, the data starts, everybody's pretty much the same age, right? 17, 18, 19, 20, 23, you know, it kind of goes up and down, pretty normal. And then at the end, we go 43, 49, 64. And although that's not normally too bad, when there's only 17 numbers, that can have a bigger contribution, right? But it was a good experiment, right? It did good 2 out of 3, which is better than anything. And we are done for that particular kind of question. So let me stop sharing and go in and look at some homework questions, which is my way of checking things. Right. Right, question 1. Consider a normal distribution, a mean of 21, a standard deviation of 3. What's the probability that a value selected at random is greater than 21? And won't that be a normal CDF question? Good to go. And they don't want percentages, so you'll type in 0.12, not 12%. Now, this guy is talking about the plot I was talking about. They're calling it a normal quantile plot, right? Here is the raw data. Here is what it looks like as a histogram. There's a kind of, I'm not convinced that's a good fitting curve, but there's the curve. When you look at the raw data, you can't tell that it's normal. Would you agree? Just a bunch of numbers could be anything. You can't see it. And if you make it a histogram, you do get a judgment call. It's not perfectly symmetric, agreed? I'm not even happy where they put the curve, but that's a different argument, right? But it doesn't need to be perfect to be usable, right? It just needs to be good enough. And so I'm not sure in this case the histogram has helped me. But would you agree that these dots are pretty linear? You know, if it's curved, it'll go dot, 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 dot up a hill, right? It'll go like that. Or up the hill and then it kind of curves, right? So when you see a sequence of dots that have a noticeable curvature to them, can you imagine a kind of S shape as well? You know, get a couple of curves. Bad news, you're not normal. Don't use normal CDFs, right? It doesn't work. Which I think might have been the problem with our data. I think our data, if we'd done that normal time plot, we would have seen a straight and then it kind of flattens off at the end kind of thing. And that would have been a good shape. So you don't get to do it, but you can get, can you imagine there could be a question that shows you a picture and the answer is this normal enough or approximately normal? You would say yes or no and go for it. This particular question has some other stuff in it. I hate the color scheme because it's so hard for me to read. Do you see this stuff in the salmon color thing? I don't know if you can read the numbers inside, it's very faint. But the mean of this data is 30.1. Its standard deviation is 0.256, and they've got some minimums and maximums, and they've got a guy called the standard error, which I'm going to tell you about later. But they have a whole load of stuff in here. They ask, well, if you look carefully, the Q1 is 29 and the Q3 is 31. So when they ask you for the interquartile range, remember it's, you know, Q3 take away Q1. You're going to look up the notes for that fella. And then using it, you decide yeses or nos. So there's 2 yeses on one of them. So I would pick that yes. Now you say, well, what about the skewness? If I look at this shape, would you agree this histogram doesn't have any distinct right or left skewedness? And very, very roughly, I guess I'd put 2 varies. I'm going for normal, not because of this, but because of this. Right, linear means you're good, right? Linear, normal quantile plot is good. And then you enter a whole load of questions which are grab a calculator and start hitting buttons. If I tell you the mean and standard deviation, can't you find X between 5 and 15, X bigger than 120, X less than 42, anything you want? Right, that's what we've been doing today. You feel comfortable with those questions? Do you want me to do one more, or you feel, yeah, we can do those? Right, they're all normal CDFs. If you were doing this one here, wouldn't it be 120, 999, 10911? Right, with a normal CDF stuck in the front of it, right? And you get the answer 0.123 or whatever they want. It looks like they keep changing the accuracy. Here it's 4 decimal places now. I think one of the earlier questions it was 3. And then they'd come back to Z-scores for whatever reason I can't tell you. I wish they'd kept the Z-scores to 6.2 and left the new stuff to 6.3. but they're mixing and matching, so we can live with that. They're talking about z-scores, and right now we're just looking at a picture. Find a z-score, such that 6% of the standard normal curve lies to the left of it. Now, if you look at these 4 pictures, which one of those 4 pictures looks like you're to the left of a z and you're about 6% of the whole cake? Kelsey? Which one of these 4?
Would it be the first one?
Yeah. Well, let's see why. Isn't this to the left of a z-score? And would you agree it's quite small? I mean, the whole cake is 100%. Maybe that looks more than 6%, but it's at the best lot. Wouldn't this one be a z-score bigger than something that was 6%? Wouldn't this have to be some big number, like I guess 94%? And wouldn't this have to be some big number, but bigger than, right? 94. So there are a big bunch of questions here where you're given the mean and standard deviation, and you're being asked to find the raw data. Okay, so let me leave that.
Question.
Yes, question.
For the one, I think it's number 7, we were just looking at it. What do they want us to put in the little box there?
Oh, you are about to find out, because we haven't done that yet.
Oh, okay.
So that was well caught, because I haven't showed you how to put what they're talking about, which is what would you need the z-score to be, right, to get you that 6% thing. So that's kind of where we're going now. So I'm just drawing their little picture because it kind of helps me as well. You got a little normal thing, right? You got an unknown z-score, but what do we know? We know that that guy there is 6%, right? And we are going to find what z-score that would be true for. Now, I can tell you how we're not going to do it, and then I'll show you how we are going to do it. Well, you could do it by trial and error. Couldn't you do a normal CDF, negative 999, choose a number like 1.8, 0, and 1. Now, because it's a normal z-score, aren't these 2 numbers guaranteed to be 0 and 1? Right, they're always 0 and 1. Now, you try that answer, and you get nothing 0.08, which is 8%. Where would I go next if I was guessing? Bigger than 1.8 or less than 1.8? Right, so
Would it be
if
less
that
than?
was 1.8 and I got 8%, what would I have to do? Move this way or that way?
We need to move less than.
Okay, less than, right? So can you imagine I would go in and I'd do 1.6. Now I could be here all day, couldn't I? But wouldn't I eventually get a number that would give you the answer I'm looking for, which is 6%, right? I mean, as a strategy, I guess it would work. Before TI-84s were invented, I guess that might have been the only strategy out there, right? You keep doing it until you get the number that works. But that's not how we're going to do it. I'm going to show you another button on our calculator, another feature. This TI-84 is worth its weight in gold, isn't it, for the number of things it does for us? There is no by hand method that you could do this process by that would really be any sense. So now, oh, I did that far too quick. Second distribution. Do you know number 2 is called normal CDF? We've used him a lot. Let's use number 3. I don't think this is going to work. I hope to crown it loud it does. I'm trying to put two kinds of calculators on the screen at the same time, and that might not work. So if you can just hang in here for a few seconds while I get the second one set up. Okay, now I'm moving this over here. I'm moving you lot here. I'm trying to minimize this darn thing. Minimize, I tell you. Okay, smaller. Now, this might not work. I promise you it might not work. I am going to try something that I don't think I've managed to do yet successfully. But there's always a first time, right? Oh, darn it, I've lost you. Where's my little go away button? Okay, there we go. I'm going to share, I hope. Oh, screen 2. Darn thing. Not sure it's worth all the hassle now. Can you see two calculators, or do you see a nice picture of, I think it's somewhere in, yeah, I know where that is.
Two
Somewhere pretty in your,
calculators.
I see two.
you can see both? Yes, I am, oh God, I deserve 4 brownie points. I have got two calculators using shared second screen. You wouldn't believe how many windows I've got open right now all over the place to just make that one thing happen. I am so happy with myself. Okay, surprising what makes me feel good, right? Second quit.
Now you got to give your dog a treat now since you did something good.
My dog should give me a treat?
No, you should give your dog a treat.
Why, if I do something good, should someone else get the benefit? My wife should make me a special meal tonight. That's what should happen. Although I'm not daft enough to say that to her. Okay, so I'm going back out both of these because I've distracted everyone to heck. And so on your TI-84, so this is literally like your physical calculator, and this thing over here is similar to the modern ones. So I want to show you the difference between them. So if you do in the modern one, you do button distribution and you go down to inverse norm and you hit enter. Now, do you see when you do that, you get this kind of screen? So some of you have got a modern TI-84 and you're looking like a guy that looks like this, right? Okay, now if you do my calculator, which is maybe the older versions that you've got, you do go to inverse norm, which is this guy, right? And it looks quite basic, right? So over here, I would like to know how to get to the left of 0.6. Remember the question was a z-score that would give me to the left of 0.6. So as a percentage, 0.6 as a decimal turns into that, right? That's 6%. So on my calculator, it's going to be 0.06. Comma. Now, they're nice. Do you see that the mean is 0 already and that the standard deviation is 1 already? Do you know I have to tell it it's 0 and 1? No biggie. Now, if you scroll down to this one, that means I'm going to find it to the left and keep away from those two. Just always use left. And then you scroll down to paste. In this case here, just finish the brackets. So do you see a slightly different format? They're saying the same thing, but you have to type them in a little bit different. Here it's kind of menus, here it's you physically type it. Now when I hit enter, fingers crossed, I get the z-score should be negative 1.55. And when I hit paste, there, do you see we get the same answer? So your answer to that question is, what goes in that box at the top? What's the missing Z value? The missing Z value in this case would be negative 1.55. Right, so I'm going to leave these guys alone and come back out for a minute. And we've got a chat here. Okay, Rachel, we are having your son sing happy birthday tomorrow. So you're going to drag him in?
Oh, probably. I would love for him to sing that.
I think kids are cute. So kids singing happy birthday is kind of fun. It will remind me of being back home when all the family are in and we're having a birthday party. There are two kinds of kids. There's the ones who won't sing for love nor money, right? You can't make, they make a racket, but the minute you ask them to sing, they clam up. And then there's the other ones you can't shut them up. They want to sing all the time. Yeah. And do you know if they're really young, when people sing happy birthday, they think it's their birthday again?
Oh, definitely. I think that's why he sings it. And then he goes, present? I'm like, oh.
Good. True story. It's came into my head. I'm getting homesick, and because I can't get back to Scotland, I think I get homesick more often than I typically do. But to give you an example of a family get together, in Scotland we have family get togethers, and it's huge. Oh, and I can share something with you. I am going to become a great uncle. One of my great nieces is having a baby. So that's pretty cool. We're already on that generation after the, God, it's trying to keep track of them. There's millions of us, almost. So that's right. So anyway, this is a story about, actually he's connected to that. It's about Hugh. He's coming up on 50 now. He's my nephew. And his daughter's the one that's having the new baby. So that makes it a great, doesn't it? Yeah. So when he was about 3 or 4 years old, we were at a family get together. It was a wedding. I should warn you that this story sounds a bit cruel, but in Scotland, I guess we're much more flexible. But anyway, he was 3 years old, and you know, kids that get bored with weddings, and it was a reception afterwards. So he just was under the table, you know. Everybody was eating and drinking and so on. He was under the table playing with some toy, and nobody really paid much mind to him because he wasn't causing trouble. And towards the end of the night, he was singing. And we were quite amazed because he's the first group. He doesn't sing, right? Happy, ain't doing it, right? 3 years, don't want to sing. And he was singing. And unfortunately, we found out what he'd been up to because we caught him. He was coming up and grabbing drinks off the table, alcoholic drinks, and drinking them at 3 years old. And he got drunk. And he was singing. And you know that if Child Protection Services had found out, we'd be in serious trouble. But it wasn't that we deliberately gave him the stuff. He just stole it on his own. And if you've ever been at a Scottish wedding, there is a lot of drink lying about in a lot of tables, so it's not hard for a kid to grab one if you're not careful. Obviously, if you see them doing it, you shout at them and scare the EBGBs off them. But he got that. I can tell you today that he still likes whiskey and he drinks it, so it didn't put him off it. But a drunk 3-year-old singing is something to behold. So that was just, yeah. He is some guy. He's the one my wife can't understand. He has such a broad accent that my wife just looks at him and smiles. Doesn't know what the heck he's saying. I've, of course, drifted, as I do. Right, focus on us. Right. That was all to do with children singing. You wouldn't believe the tenuous connection here. So we are going to look at some more examples of finding those missing Z-scores, right? And then we're going to expand that to finding missing X-scores that do the same job. So where are we? Advanced, double click. Okay, where's my white screen? I've lost it. You're looking at a white screen, agreed? Okay, check time, we're good. So I'll do it visually because it helps me. Suppose I want to know a z-score over here, and I want to know the z-score so that that chunk of space, right, that big chunk of space there is 0.85, which I would call 85%, right? Now, would you agree that's a shaded to the left? And so the inverse norm calculation will tell me the z-score that will give you 85% of the data to the left. So that's going to be an inverse norm. Okay. 0.85, because you always write 0.85, not 85. You always do it as a decimal. And 0 and 1. And then bingo, right? Now, I'm not going to go out and in. I'm just going to do it. And if you can do it with me, that would be great. So if I screw up, you'll tell me I got the wrong answer. I'm doing an inverse norm as we speak. I'm putting a 0.85 in. I'm doing a comma, a 0, a comma, and a 1. And I am looking at a z-score of about 1.04 if you round it off. And I got a nod on that, so I am happy. Do you feel comfortable about answering questions like this? What's the z-score that makes 80% or 8% or whatever the number is, right? Next.
Are you always finding to the, see how to ask this, like to the left of the z-score?
No,
for
you're
inverse
not,
norm?
unfortunately. There's another half of the questions where you find to the right.
Is inverse norm used for that too?
Yes, but you do a little
okay.
tweak.
Okay.
So let's see if you can guess the tweak. So I'm going to, for no reason at all except I want to, I'll change the color to red. And I want to find a z-score so that the bit to the right is 0.123, which is what, 12.3%, right? Now, I'm going to use the inverse norm, but I have to do a tweak. The inverse norm only tells you things to the left. I don't want to know the thing to the left. I want to know the thing to the right. But couldn't I change this question to find the white bit? And that would be the same z-score. So what I'm thinking is, although that is what z-score gives you 0.123 to the right, isn't that the same as finding 0.877 to the left? So do you see that when you use the inverse norm, you are going to, the tweak is to find the other answer. But won't that answer be the same z-score as the one you are wanting? Does that make sense? I'm looking for this, but I find that. And that's the same z-score. So now we can use our z-score, and it should work. So I'm doing an inverse norm thing. And this time, we're looking for a 0.877, comma, a 0, comma, a 1. And the z-score I've got here is 1.16. Yeah, that'll do.
I have a question.
Yes.
Will they always have the same z-score on both sides, or is it just for this case? I'm gonna look at that.
Oh, what I'm saying is that in this case here, yes, they're the same. A z-score that gives you 0.123 to the right is the same z-score that will give you 0.877 to the left. Can you see the connection between these two decimals? They're not random.
Mm-hmm.
It's what's left from one, right?
If this were to be a homework problem, would the 0.877 be already there, or would we have to find that?
No, you would be given the 0.123 and you'd have to figure out that the number you have to use is 0.877.
Okay.
Right? So can you imagine this was a homework, not just a homework question, but say a final exam question? Your working would not have an awful lot of working in it. Wouldn't you write down this to tell me why you're using, I just did that the wrong way around, sorry. Wouldn't you be telling me this to explain why that number is used? Although you could probably do it in your head, wouldn't it be worthwhile just to do that in a an exam situation. Now, in a homework situation, couldn't you just do it in your head and it wouldn't really matter? Okay, let's try another one of these. I would like to know a Z-score so that the guy to the right is 0.11. Now I'm going to have to use a normal CDF with some decimal, 0 and 1, right? In this question, do I use 0.11 or do I use another decimal? And if I do, what would that other decimal be? How would I get the Z-score that makes this happen?
Oh wait, isn't that supposed to be inverse norm instead of normal CDF?
Did you all catch that deliberate mistake? Okay, back to my question. What number do I use? What decimal do I use?
0.89.
Right, suppose it was this question. What do I use?
.69.
Do we?
No, we use that 0.31 because of the left, right?
Right, correct. Shouldn't say right in these questions. Do you see the difference? If you want to find something to the left, that's the number that you use because the area to the left is 0.31. If you want to find the area to the right, don't you have to find the complement, I guess you would call it, the complement of that, which is 0.89. There are only two questions in the world, really, right? Correct. Only two questions in the world. Z-scores that you need that give you an area to the right and Z-scores that you need that give you the area to the left.
Professor Robertson?
Yes.
So they will specify in the question to the left or to the right, and that's how we'll know inverse not,
Or
right?
they'll give you a picture and you can see it.
Okay.
Right, if they don't tell you left or right, the question's not fair because then you don't know which to use, right? Now they can phrase it all sorts of ways. Couldn't they say bigger than or less than? You know, some greater than, more than. I mean, various English conversions, but they all mean the same thing, right? They could do it that way.
So I have a question for how you find 8.9, the complement. Is it that you're subtracting 0.11 from 100, or how you're finding that? Because my mind's just not figuring that out right now.
I keep doing it, the answer to the question. You take the number away from 1.
Okay, that's what it was. Okay.
That's where it came from.
Got it. Okay, thank you.
You're welcome.
And on the modern calculators, it just, you don't have to like figure any of that out. It just says left, center, or right.
Well, you could choose that, and that's fine. But since not everybody has that calculator, I'm just doing it one way. That way I can do it one way for everyone and you can tweak it. But yeah, you could tweak it if you've got the modern calculator. But then you have to remember left or right. So I guess you still have to remember something. Are we good with that kind of question? So if somebody said, find a Z-score that gave you an area to the left of, 12% or give you the area to the right of 12%, you're quite comfortable about the inverse norm CDF calculation that you would need to do. Okay. I want to find out if sampling distribution is happening yet. If it is, then I'll show you. If not, I've got some other thing I want to show you before that. Okay, that's good stuff. That's good stuff. And that's basically, that's a picture, right? 77 to the left. So you see it's telling you the percentage and it's the percentage to the left. So it'd probably be what, that picture? And then inverse norm in the usual way. Right, so won't that one be to the left of, so you just use the number 0.77. You wouldn't change it. If it had been to the right of, you would have to do something like that. Now, that's another to the left, so it'd probably be this answer. That's to the right. Okay. So which one of these four pictures would be a z-score so that 6% of it is to the right? Actually, I just did that one. What am I talking about? Let's do a better one. Right, let's 11. 65% of it to the right. Which one of those four pictures do you think would represent 65% to the right?
The fourth one?
I agree. Now let's look at the clues. First, it's to the right, so we can throw away those two, right? Because those are shading to the left. Now, between these two choices, they are pretty similar looking. Why did I choose this one for the 65% and not the one above it? Because they look very, very similar, but this one's right and that one's not. There's a clue there somewhere.
Well, 0 like is halfway point, so you know half of it is 50, and then just a little bit more would be 65.
Couldn't have said it better myself, right? Agreed? That's how you know. Now, if they had said, let's just change that question. Pretend for a minute they'd said 45%, right? So they wanted a Z such that 45% would be to the right. Wouldn't it still be these two pictures? But wouldn't 45% be that one for a similar kind of argument? So there's a lot of nuance there. Now, apart from that, wouldn't that also, this question, back to the 65%er, would that be an inverse norm with 65 in it, 0.65, or would that be an inverse norm with 0.35 in it? What would we use in that question, at least in the way I showed you today? 0.65 or 0.35 for these questions? You're pointing, but I can't hear you.
0.35.
Correct. If it's to the right, you do a subtraction. How about that as a little sentence, right? If it's to the right, you do a subtraction. And if it's to the left, you leave it alone. Oh, that rhymes. Left, leave it. Right, left, you leave it. That'll work for me. Okay. Now, what we're hitting here in question 12 are, we're back to normal CDFs again. So the homework jumps from normal CDFs, inverse norm CDFs. Now we're back to normal CDFs. Do you see in these questions, what we're looking at are essentially word puzzles and stories, but you still end up finding bigger than this, less than that, or between these two, right? So that's kind of what's happening in the questions that you see as we go through quite a few of these. So let me wind back and kind of take you through that process. So we're just going to make up our own. So let's suppose we're doing potassium level, and I'm making up numbers. You don't know this because it's not true, but the mean potassium level is 35 for an adult male, a normal, healthy adult male, right? And that the standard deviation is 5 for an adult male. And what's the probability, or what percentage? Probability and percentage are interchangeable here. That you get someone, right, and you test, and they end up being a potassium level that's greater than 53. So what percentage of adult males would have a potassium level greater than 53. Well, isn't this a normal CDF question? Now, I need a low, I need a high, I need a mean, and I need a standard deviation. Okay, bigger than 53. Where does the 53 go? First or second?
First.
Okay, and 53 or bigger. You see, it works that way. Bigger, right? Well, I'm zooming into the calculator. Somebody wants to do it with me and tell me I'm right. That would be great. So it's normal CDF. We're back to that guy. I'm typing in 53,999, 35,5, and I am looking at, whoa, that's interesting. I am looking at 1.59 e to the negative 4. Are you looking at that? That's not wrong. That's just a very small number. That is scientific notation. That's the way the calculator does that. I hope you've taken a chemistry class or a physics class where weird numbers like that appear. Now, to turn it into human numbers, oops, it's that guy. 0.3 more zeros, 159. Even when I make it a percentage, can you see that that person, his potassium level, what, 0.015% of the population would have that. That's like 1 in 10,000 people would have that kind of number. Wouldn't that be, ooh, we better have a good look at you, because this is not good, right? This would be, you know, in that chart where they do the potassium level and they have normal, high, and, you know, red lights flashing level. I mean, this guy's red lights flashing, horns going off, and all sorts of things. This would be a really serious number for you to come back with. And so they would be highly concerned about your potassium level, right? Or anybody with that or bigger even, right? Because that's kind of what we do here. That means now that, don't we have a feature, a way of calculating how unlikely, right, what percentage of people would have a particular value? Okay, this one I'm trying to not make accurate. I am trying to make accurate. Does anybody know what the average weight of a baby is? A normal, not preemie baby. Some of you have had them. So what's the going rate right now for babies?
8 pounds.
8 pounds, okay. Standard deviation, I'm going to have to guess this, right? So let's do a standard deviation of 0.7. Right? And this I can tell you for true. My mum had 10 babies, and I was a 12-pounder. Rachel's face does not.
Oh
look.
my goodness, you were not. Your poor mother.
Ouch. Look at the same thing.
What, Leah? You had a baby that size?
I've never had a baby that size. I would tell them to cut me open before I push a baby out of my little self.
Okay. No, my mum, I guess I do feel sorry. I mean, she's passed away now, but I think she'll forgive me because she kind of liked me. So let's do this one. What would that look like then? In our story then, a normal CDF would be a mean of 8. Oh, yeah. Get this right. 12 or bigger. Then a mean of 8, and then a 0.7. Based on the data that I've supplied, this is not going to look good for me, is it? So I'm getting a normal CDF with 12 or bigger, so 999, working on an average of 8 and a standard deviation of 0.7. And if that standard deviation is correct, my answer is ridiculous. My mum could have won the lottery easier than having me. I strongly suspect that this number here is much bigger than I've got. So I'm going to make a different prediction. Let's suppose that the real standard deviation was a lot larger, right, 2. Then my normal CDF will still be 12, will still be 999, will still be 8, but now I'll change that to 2. So that will make a little bit of difference to what my answer would look like. And this time I end up being 0.023, which is about 2.3% of the time. I like that answer better. Now, you can tell, or you can gather information that is that. And the reason that they gather information like that is so that when babies' weights are collected, don't they weigh the baby? One of the things they'll do when a baby's born, right, they'll check its breathing and all the other good stuff. But isn't one of the first things they do is check its weight? Because that's a very good indication of, you know, how healthy our baby is, right? If it's a preemie, won't it come out at, you know, 2 pounds 5 ounces or something, and that would be a concern. So anyway, you would do that weight. And in fact, when your child is growing up and it's getting its, I don't know what they call it in America, is it pretty typical, it is in Britain anyway, that every year your child gets a basic checkup? I call it the MOT test. So your child gets in and he gets weighed and they check his hearing and his eyesight and, you know, all that good stuff. And
it's like a Wells child visit is what it's called.
What, Wells, as in wellness kind of well?
Yeah, like a Wells
right.
child.
So, right, is that something that you basically you're expected to do, or is it much more mandated than that? Because in Britain, you get a card through the mail saying it's time for your child's yearly checkup. They tell you you better bring it in, because if you don't bring your child in, then what you would call child protection services will come and visit you.
Yeah, no, they don't really do that. And normally, like, the doctor's office will bug you and bug you and bug you until you make an appointment.
Well, they would bug you, but if eventually you didn't do it, they would send someone. In fact, Britain's a little bit different than America, because this kind of semi-shocked me. Do you know in Britain, when your baby is born and you take your baby home, for want of a better word, we give different names to these people, but essentially a social worker comes to your house when you've got a new baby, and they check your house out. So they check it, is it clean? You know, if it's dogs' feces everywhere and cats crawling all over the place. They check your fridge. Do you have food? Do you have baby formula? Do you have children's clothes? They basically check it out, and to make sure that that baby is being put in an environment that's healthy and safe, and you're nurturing. You don't need to be rich to do that. I mean, the government, if you don't have enough money, the government does supply almost all of that. You know, baby formula that could cost you a fortune, you get it for free, you know, if you don't have the money. So, you know, that's the other side of it. But if you don't look after your baby, they will do something about it. And not looking after your baby includes not sending them for checkups. Now, I guess you could have religious grounds for not getting certain things done to your child. You know, some people don't like their child being vaccinated. Some people don't like blood being taken from their child. You know, certain religions have issues with, you know, certain things that they will allow and won't allow. And they are pretty accommodating to that, but you know, they are more forceful about what is treated as normal. See, because it's always been the case, nobody thinks it's a big idea. Oh, you've just had the baby. Has the woman been around to check your house yet? Yeah, she's coming on Tuesday. You know, people don't. It's not a stigma, because millionaires have to have it done to them as well. Right? It's everybody has to get it done. It's like a regulation. It's pretty good regulation, in my opinion. Even although, you know, I dislike governments, there are certain things they should do, which I think that's one of them. Because children can't look after themselves. And so sometimes parents are probably, for some horrible reason, not good parents. While I'm drifting, do you know why this isn't a joke, but it's a kind of statement. Do you know why new baby smells? There is a thing called, do you know there's a new car smell? There's a thing called the new baby smell.
Oh yeah, in their hair. It smells so good.
It is. When they bring round, in our family, there's a tradition when the baby gets born, I'll miss it because that one that's going to get born, when she gets born, there's going to be a family get together and everybody gets to hold the baby and do all that cool stuff. New baby smells, they smell so cool. It can't just be me, right? Leah, it can't just be us.
No.
There's a new baby smell, right? They just smell good.
It's a lot of people who are like secretly likes the smell of babies, and when they're around babies, they kind of sniff them just a little bit.
Okay, in case you think I'm weird, then I'm not that weird. Anyway, do you know the reason why they smell good? It's so you won't eat them. It's a protective device. New babies are cute and they smell good, and that's to stop them away back in the day from being eaten by their parents. I'm sure that's a defensive mechanism. Marie's not sure if I'm being serious or not. Okay. God, I lose the place so often. Right, where are we in the big scheme of things? We're almost finished, aren't we? It's 25 past. So I guess I'll round off. That's probably a good closing point. In the future, we're going to look at calculating things called percentiles. So imagine you had an IQ test and you wanted to know what kind of IQ would put me in the top 5% of people, right? That kind of question. We're going to be looking at things like that. We're also going to be looking at what's called the sampling distribution. That's going to be a biggie. And the sampling distribution says, suppose you take a sample of 100 people and you find the mean. If you take another sample of 100 different people, won't the mean age be different each time? They'll be close to each other, but there will be differences, right? And can you imagine you took a sample of 100, hundreds upon hundreds upon hundreds of times? That would give you a sampling distribution. And your sampling distribution is always normal. And it doesn't care whether the population data is skewed left, skewed right, or got funny bumps in it. The sampling distribution, the distribution you get when you take 100 people and just find the average of them, right? That distribution, called the sampling distribution, is always normal. Phenomenal feature, you wouldn't have expected it. You would think, hey, if the data's skewed to the right, shouldn't, you know, all the means and things end up skewed to the right? And strangely enough, they're not. It's a really interesting fact. It's called the sampling distribution. And its mean is the same number as the population mean, which doesn't surprise you. Would you agree that if you were calculating a lot of means, wouldn't you expect the mean of the means to be the population mean, right? It's like taking a huge sample. And the standard deviation is sigma divided by the square root of n, where n is whatever the sample size is. So if I'm doing sample sizes of lots and lots of samples of 100, then the standard deviation would be that. What that tells us is, if you take big samples, won't that be a small number? Sigma over square root of 1,000,000 is a small number, right? What that tells us is, if you do really big samples, you can do very accurate predictions about what the mean of the population is. You can make inferences that it's likely 99% of the time between two very small ranges. And that, eventually, a version of that leads to the kind of questions that we're probably going to get inundated with. Do you know when they do polls and they say we've conducted a poll and 45% of the people are going to vote Republican and the margin of error is 2%, you know, that kind of thing? That comes out of the sampling distribution, those numbers. So we'll actually find out where those...
I have the urge to bite my child.
You have an urge to do what? Rachel? Maybe you didn't want to share
Nothing.
that.
I was looking something up because I could tell you after this
Okay.
episode, but it's pretty interesting.
Is it to do with babies smell good?
No, if so, a while back ago, when my son was like 2 or 1, I was telling him, I was like, I just want to bite my son's cheeks and like just pinch his cheeks and stuff. And I looked it up because he's like, you're so crazy. You gotta keep my kid away from you. I was like, well, I looked it up a while ago and I had to look it up again because it's called cute aggression and it's completely like normal and it's scientific and everything. But I was like looking it up. I was like, why do I have the urge to bite my kid again?
I don't have that one, but I guess there's different ones. There are lots of ones. Do you not have the urge to, when you have brand new babies, just to hold their hands so they're so tiny?
Oh, I know.
They're just so cute. And you stick your little finger on it and they do the grip of death, you know? One of the first things that babies learn to do is the grip reflex. In fact, when you get a baby checked, that's one of the things the doctor will do. They'll try and see if that reflex is still there. Basically, if you stick anything in a child's hand, they will grip it, right? It's a kind of, they don't even think about it. It's one of their reflexes that they do, and it's a good reflection on child development. It's one of the tests. They do other little tests. Do you know the one where you take your finger and you go along the sole of a children's feet and they curl their toes? And that's a good test for reactions. What you're looking for is, because kids can't tell you things, so you have to do it other ways. And so you're trying to look for neurological issues, because if they don't have those reactions, there might be something serious that you need to look into. You know, it could be just could be you've just got a lazy baby that's not ticklish, right? It could be nothing, but you know, it might be something serious. They've done. I did a class in psychology about babies. Part of it was to do with babies, and they're fascinating. The thing. Do you know babies have an inbuilt reaction to not crawl off tables? They have a they got an experiment. They put a glass perspex, whatever it was, on top of a table. So underneath it was a table, but as you walked to the edge, it would have looked like you would drop. You can put babies that crawl, right, are just learning to crawl on that table, and they will crawl. But see, when they see the edge, most of them will stop. They will not walk over the edge, right? They won't crawl over it. So they already have a depth perception that sharp lines and edges are dangerous, and they try not to walk over them. That's one of the ways in which they, another test that they can do on children. I don't know if they do it in America, but they've got all sorts of little cute tests. Do you know babies get used to their mother's voice really quickly? In fact, some babies know their mother's voice before they're born.
Oh yeah, I feel like it's because of being in the womb.
Exactly. It takes them a bit longer to get used to their dad's voice. And surprising enough, they don't recognize their mum's features. I think, don't quote me on this, until they're 6 months old. Up to 6 months olds, anything will look like their mum. It's their voice that makes them know it's you. A face just looks like, I don't know if it's their visual thing hasn't developed yet, you know, so that everything's blurred or whatever, I don't know. But it takes a child about 6 months before he physically can recognize you. You know, they show you pictures of people and the baby doesn't react, because even if it's your mum, but after a certain age, when they put a picture of you up, the baby recognizes you. So there are lots of little features like that.
Yeah, I think that's pretty neat. No, it kind of reminds me of like when my son would look at me when he was like, you know, months old, like, who are you? Why are you holding me?
Okay. But as long as you talk to them, they were really happy, right?
Oh, definitely.
So they could hear you. So that was comforting.
Mm-hmm. But yeah, that's what I was looking up. I had baby on the mind still.
Okay. Well, I'm sorry for keeping you all along, but we did get to hear lots of things about babies, and that is good. But remember, don't have babies until you're in a good, solid relationship, because that's a good way of screwing up your life, right? So I'm being your dad here, right? Don't have babies until you are in a stable relationship, whatever that means to you. Okay? Daddy advice. Right? I'll see you tomorrow. Bye-bye. Anybody who want to hang about as always or ask a question, I'll hang about for you.
Do you
I
have
have a
any
question.
babies of your own?
No, we have fur babies. Unfortunately, God wasn't generous to us, but you know that's life. You do what you do. But I kind of surrogately love all my nieces and nephews, so that kind of works. It makes up for it. So when I get back to Scotland next year, thank goodness next year I'll get back to Scotland, I'll have a look at the new baby, and it'll still, well, it won't have a new baby smell, but it'll still be quite cool.
I do have a question.
Yes.
After you grade the midterms, will you be sending out accumulative grades like from homework and the test together to us?
Yes.
Oh, awesome.
That was a nice, easy answer.
I have a question on the sampling distribution picture that you wrote.
This thing?
So is the reason the mu button is not on the calculator because the sampling mean can be the same as or around the same
Right, the way you
as the
calculate it is
population mean?
identical. Let me say it that
Okay.
way. Right.
Okay.
If you do a sample, you add them up and divide by how many. If you do a population mean, you add them up and you divide by how many. But when you do the standard deviation, which is the second guy, when it's a sample, you know, not this formula, but when you look at the formula, you divide by n minus 1. You remember we never did it, but the whole other stuff you divide by n minus 1. That's only true if it's a sample. You only divide by n if it's a population. So the two numbers will be different.
Okay.
That's why there's an SX and a sigma. Those numbers, when you treat the data as a sample compared to a population,